Well, thank you all for joining another lecture for interactive computer graphics. Today's lecture is going to be on an exciting topic that is going to be, drum roll, GPU ray tracing. Now, this is not a very new thing, actually. People have been implementing ray tracing on the GPU for quite some time now. Like as soon as we had programmable GPUs that we could implement anything that we want, one of the first things that people wanted to implement was ray tracing. So they did that. But this is becoming new in the sense that now we have direct hardware support for GPU ray tracing on a larger scale than we did in the past. So that's definitely something that's emerging in that sense. All right, let's talk about let's start here. I'm starting with this because this seems like a very popular comparison. Like whenever people are talking about rasterization versus ray tracing, they start with this image. It's super popular. I believe this is from an earlier Intel presentation, but I'm not 100% sure. It may not be. I'm not sure exactly what the source of this image is, but people like to start with comparing rasterization and ray tracing, and I'm going to start there as well. And I'm going to use the same image, and you see like rasterization, just primary visibility here, and pretty much nothing else. Over here in ray tracing, we have nice shadows, we have reflections, and everything is looking much nicer. Although this is a little bit misleading, because we know, you know, we can do a bit more than just this with rasterization, right? We did this in this class. Like we showed, for example, how to do reflections, right? So it's not like we don't have any reflections in rasterization. It's just they're computed differently. They have certain limitations. Shadows. It's not like we don't have any shadows with rasterization, right? So this is a little misleading. Yeah, true, but a little misleading because there are things that we can do in rasterization to make that a bit better. But what's happening today is that when we think about how people use the ray tracing support on the GPU, it's not ray traces versus rasterization. It's more like rasterization plus ray tracing. Right? So that we're combining rasterization and ray tracing. That's how it's used in practice today. So here's a scene from a very recent game, Cyberpunk, and this scene is rendered using two different techniques. Well, one of them is using just rasterization. The other one is using rasterization plus ray tracing. And I'm not showing you which one is which. Looking at this image, can you tell? Now, ray tracing is supposed to be a huge deal, right? And it is a big deal. But just looking at an image like this, it's not immediately obvious which one uses ray tracing and which one doesn't, right? Because there are things that we can do with rasterization without using any ray tracing at all that produces this somewhat comparable image. But I'm going to say that this is also a little bit unfair. But can you tell which one's which? Soft shadows? Yeah, it's difficult to tell. You might be surprised, but this one has ray tracing. This one is computed without ray tracing. Well, without GPU, without RTX, or without the XR is what I'm trying to say. This is, I believe this is using screen space ray tracing, so it's some sort of ray tracing, but it's more in the raster context. It's not using like pure ray tracing. But you can't, you look at this image, and this doesn't quite sell ray tracing, right? Obviously, you might even arguably prefer this one over this one, right? It's kind of, yeah, maybe you like these crisp reflections. They look really nice here. Maybe you think that reflections are supposed to be a little bit blurry. It becomes a matter of taste in a way, right? So this is not a fair comparison either in the context of like showcasing ray tracing. And the reason for this is that these games that we have today, they're not really designed for ray tracing. Ray tracing is oftentimes added like an afterthought. It's not necessarily an afterthought, but if you imagine their user base, most people playing these games will be seeing this. Like they will be running those games on hardware without hardware ray tracing support, right? So most of the players will see this. So if you are a game developer, of course you're going to sort of optimize your production process for this. But then you want to give a little bit of extra for people who have access to hardware ray tracing, so you add stuff on top. So it's very different in the sense that you can't just get something that doesn't look right without ray tracing, right? So you kind of need to develop your scene accordingly. That's why this is not a fair comparison for ray tracing. But with ray tracing, though, today we can do really, really amazing things. Like this image is rendered using a very large number of light sources. I don't even know how many. And it's just looking gorgeous, absolutely gorgeous. Like this kind of lighting would be very difficult, very, very expensive to compute using rasterization. Because if I were to use just rasterization only techniques for an image like this, and if I have a lot of light sources, I'm going to have to compute a lot of shadow maps, right? And that would be very, very expensive. It wouldn't be fast at all. But with ray tracing support, we can do that. So today, what we do is that we handle primary visibility with rasterization, and all the secondary effects like shadows and reflections using ray tracing, right? Nonetheless, you look at this image, it looks great. I love it. It's absolutely gorgeous. But it doesn't look like it's a photograph, right? It's not real. I mean, you can tell that it still looks a little bit CG. So that's the thing. Like with ray tracing, we're supposed to break that CG look completely. We're supposed to get something that looks like real. We're not quite there yet. There are multiple reasons for that. Like one big reason for this scene specifically is that probably these materials could be improved. So yeah, ray tracing improves the lighting and shadows and reflections, but the material definitions probably require a little bit of improvement here. But there's a lot more. Like there's going from here to something like this with offline ray tracing. Now look at this image. Honestly, I know that this image was rendered using Arnold, but I don't know what part of this image is real, what part is CG. It's like, look, I really don't know. Look at this image, it's like impossible to tell. But this is offline ray tracing, right? So this is really using ray tracing to its full capacity. So eventually, this is where we want to end up with interactive rendering, but we're not quite there yet. And I'll explain why that is the case. So we're going to talk about GPU ray tracing today, and basically what I would like to cover is why. Why do we want GPU ray tracing? Why is this a big deal? It's a huge deal, and why is that? How does it work? How is the hardware sort of structured, like the ray tracing pipeline is structured? What can we do now? And what should we expect the future to look like, possibly throughout your careers? All right, that's going to be our topic. But let's start with, again, going back to rasterization versus ray tracing. So you see that in this course, I've mentioned ray tracing a lot, even though our main topic has always been rasterization, right? Because the GPU we're using for interactive computer graphics is designed to do rasterization. But I kept mentioning ray tracing because it's everything that we want to do with rendering. We kind of have to, we end up looking at ray tracing in some way or another. So these two algorithms are actually conceptually very similar to each other. It's just like the inverse way of looking at things. So it's like, you can think of this rasterization as like a nested for loop. Like for each primitive, you find the pixel samples. That is for each primitive, for each pixel, right? Sort of. With ray tracing, it's like for each pixel sample, for each pixel, you'll look at the primitives, you find the closest primitives. So it's like for each pixel, for each primitive. So it's like the same nested for loop, but in the inverse order. It really looks like that from a distance. So it's okay to think about ray tracing and rasterization as like the opposite operation. So rasterization starts with the triangles that we want to render and goes to the image, and ray tracing starts with the samples that we have and finds the triangles, right? So let's remember how these two algorithms work in the context of primary visibility. So with rasterization, I have my triangle, and I'm going to project that triangle and find it where it is in the canonical view volume that's on the screen, and I get my next triangle, and I then find its position on the screen, and with using z-buffer rasterization, I can figure out which triangle is in front of the other, right? So that's how rasterization works. With ray tracing, we went over this before. We start with having our scene, our entire scene, and then we're going to, actually we don't even need this linear scene canonical view volume kind of stuff at all. So like with ray tracing, we don't need that. Well, what I need to know is where my sample is on the screen that I'm interested in, and so that I can send a ray through it, and that ray, I will traverse that ray, and I'll find the hit points with the first hit point on a triangle or a scene primitive, and then I'm going to shade that point, right? And if that triangle is semi-transparent, I can just continue, right? I can just take this ray and continue and find the next one. So this handling transparency becomes something super easy in the context of ray tracing, right? It's really nice. And if I want to form an image, I just need to send samples through each one of my pixels, and in the end, I have my image. But we said the power of ray tracing is not about primary visibility. Like rasterization is about primary visibility, but ray tracing can do more, right? With ray tracing, yes, we can generate a primary ray and send it through the scene and find a hit point, but we can also, at that point, we can also send secondary rays, right? Like a secondary reflection ray. And by tracing that ray and finding the hit points, we can actually compute reflections. We can actually properly compute reflections. So we talked about this, and ray tracing shines with its ability to do things that are just way beyond primary visibility. Like we can handle reflections, refractions, and shadows, and realistic illumination, that is global illumination. So that's where ray tracing really shows extra advantages over rasterization. So that's the reason why, one of the reasons why we want to use ray tracing, right? So we want to do shadows. Yeah, we can do shadow maps. Shadow maps work. Like we can find the position for any point on the depth map and then figure out where the shadow is, and we can get some shadow that looks like this, and that would be fine. But with ray tracing, we can actually improve this quite a bit, because we're not going to have, we won't need to pre-compute a depth map with some resolution. Instead, we send shadow rays, and with those shadow rays, we can actually compute these hard shadows in a very nice and crisp way. Look at this, right? So we can have very sharp shadow boundaries if you're using ray tracing. But maybe you think that shadow maps are good enough. Maybe you don't mind. Okay, for point light source, that works. But how about area lights? When I have an area light, I'm going to have an area shadow, right? With rasterization, that doesn't work so well, right? With shadow maps. But with ray tracing, I can just send rays to my area light source at multiple different locations. And by doing that, I can figure out which portion of this light is covered at any point in the scene, and that will give me nice soft shadows. And with ray tracing, I can do that. I can sort of fake soft shadows with rasterization-based approaches. We talked about a couple of them. There are others, but they're not going to be perfect, right? They're sort of okay. They produce something that looks soft, but they always have one problem or another, right? Same goes with reflections. We can do reflections with rasterization. We use cube map reflections, for example, for objects. I showed you how to do this, right? So we're rendering faces of cube maps, but this is not going to be the right reflection, right? This is going to be sort of fake, because this cube map reflections, they're only correct for this one point in the middle of this object, but it's going to be incorrect for any point on the surface. Actually, even for this point, it's not reflecting the teapot itself. So there's no reflections of the teapot itself on the teapot, which is sort of weird. It's not what is supposed to happen. So like I can see the reflection of the spout here, or I can see the reflection of the handle back there because, well, that's not in my cube map, right? But if you use ray tracing, you can actually see these. You see that the reflection of the handle is over here. So I'm going to show a few images from the teapot rendering competition from prior years. Some award-winning images you'll see throughout this lecture today. So, all right, this is a little subtle, but you know it's important for it to be there. Here's another example where the reflection is less subtle. You can actually see it. I mean, you may like it or you may not like it. Nonetheless, it's supposed to be there, right? That's how reflections work. So, but you know, maybe with simple objects, we could handle reflections of this sort. Maybe. Yeah, this is with ray tracing. It's computed using ray tracing, so there's proper reflections. But maybe, yeah, maybe these edges will be a little bit problematic. But you know, most of the surface maybe we could handle, right? But these are, remember, these are perfect reflections. That is, perfectly smooth surfaces. What if the surface is not perfectly smooth? If the surface is not perfectly smooth, then the reflections will look more like this, right? So handling something like this for an arbitrary object, that would require using ray tracing if you were to compute this properly. Of course, we could try to fake this by trying to blur the reflections, but it's not going to be exactly the same, right? And with ray tracing, we can render something like this. But also we can evaluate materials. Like in this case, it's polished aluminum, I believe. But if it's brushed, this is what it's going to look like. And we can actually properly compute this using ray tracing. That's where the advantage is. So can we fake this using rasterization? Probably we can produce something that kind of maybe looks like something like this. But that would be a lot more involved and it won't look exactly the same, obviously. So you always lose some quality when you're trying to fake something like this. But how is this even helping? Like where is this coming from? Like this is all related to the rendering equation. We talked about the rendering equation a lot in this course. This is the rendering equation. This is the incoming light to a point, and the incoming light is going to be the sum of direct illumination coming directly from the light sources and indirect illumination, right? Indirect illumination, that's basically reflected light off of the objects. And we oftentimes separate the two and handle direct illumination and indirect illumination as separate integrals, as sum of two separate integrals. For handling our reflections, remember, we did a trick. We changed this BRDF. We changed this material function and we replaced it with a delta BRDF. With delta BRDF, things simplified because delta BRDF was 0 for all of these directions except for this one perfect reflection direction. So with perfect reflection direction, we basically got rid of this whole integral and everything collapsed into just this one light coming from one direction. So we could sort of handle things like smooth reflections like this. But if you were to compute materials, if you were to handle materials not that smooth, still have strong reflections, but not smooth, then we're going to have to do a bit more. That's not going to cut it, right? And these sort of materials are quite common in reality. They are actually all over the place, right? Not every reflective surface we have is smooth. And almost all of the surfaces that we encounter in a daily life will have some sort of reflection. Some of them will have very obvious reflections. Some of them will have more subtle reflections. And oftentimes those reflections are not going to be perfect. So same goes with refractions, right? With smooth surfaces, maybe we could handle them with some image space diffraction techniques, but you know, materials like this are a lot harder to handle. Right? So like in a scene with all sorts of complex materials, you really need to use ray tracing to get the image quality that you want, right? But going back, yeah, soft shadows versus hard shadows. With rasterization, we could hard shadow. Maybe we could just blur it in a little bit. It doesn't look quite exactly the same, right? But we're trying to get an image that looks sort of similar. And with reflections, yeah, we could do this like with perfectly flat objects or with cube maps. If it's not perfectly flat, maybe we can fake it, but we're not going to get exactly the same thing. Right? We could still do something with rasterization. With global illumination, right? So we could compute global illumination with ray tracing. We could actually with global illumination we're stuck. We don't have a rasterization-based solution for global illumination at all. So this is actually all right, let me rephrase it. We don't have good rasterization-based solutions for global illumination. That there are solutions, yes, and I'll show you one, but they're not necessarily good ones. So we're kind of stuck with ray tracing. Now this is real-time global illumination. Yes, computed on the GPU, but it is using GPU ray tracing. So there's ray tracing in here. Okay? All right. So let's see the graphics pipeline and GPU graphics pipeline and how this whole thing works. All right. So rasterization pipeline, you guys are familiar with this. So we have some input primitives. They go through vertex processing, vertex shaders. We can have a tessellation shaders. We can have geometry shader, whatever. Some vertex processing happens here. Some rasterization comes after that, and then we have fragment shader, and then we have our final image. So you might expect the ray tracing based pipeline on the GPU to look similar. It doesn't look completely dissimilar, but it's not quite like this, right? It's not like we're just sending pixels and then we just generate some rays and then we have some hardware supported ray tracing happening in between, and then we have hit miss shaders, basically equivalent of fragment shaders that computing the color, and then we have final image. It's kind of like this, but not quite. Not quite. So we're going to have to modify things a little bit to fit the way that ray tracing works. Actually, this could work. But the reason why the GPU graphics pipeline for ray tracing is not quite structured this way, just like an exact replica of the rasterization pipeline. It's not quite like this because we want to be able to do more with ray tracing. So the goal of ray tracing on the GPU is not to take this pipeline and replace it with ray tracing. That's not the goal. We're going to use ray tracing in combination with rasterization, and we're going to use ray tracing mostly for secondary effects, right? Like reflections, like shadows. So the goal of ray tracing is not going to be just directly producing this image. So we're not going to spit out this image from whenever we compute these colors, but we're going to send it back to our ray generation. So whatever color we compute here is going to be sent back to whoever generated that ray. Because if we are generating a reflection ray, I would like to know that reflection amount coming from that direction. I send the ray and I get the amount of reflection from that direction, and then I'm going to use it in my shading. So I need that color back here so I can actually use it, right? And I'm not going to directly output that color because that's not necessarily my primary visibility, right? That could be my secondary visibility. That could be shadows, right? So I need to know that, is this when I cast a shadow ray, I need the result of that shadow ray back from where I'm sending that shadow. So in the end, I'm going to get it back, I'm going to get all the secondary stuff back, and then I am going to produce my final image. So my final image is actually going to come out from here, like wherever I generated my rays. So that's what the ray tracing pipeline looks more like. So let's take a look at the ray tracing pipeline in a bit more detail. So particularly what happens in here, this magical stuff. In here, in the ray tracing box, let me blow it up a little bit and show you what goes on in here. So there's going to be some input and there's going to be some output, of course, like it's connected here. So what's going to happen is that at first, when we send a ray into this ray tracing box, the ray is going to be used for traversing the scene. So it's going to go through the scene and find the primitives. How is that going to do that? Well, there's going to be some dedicated hardware support to help with this process. It will, of course, need to have some access to our scene definition. So this will need to know our scene, and I'll say a few more things about that in a little bit. That's why I sort of made this box a little bluish, right? Because it's like our scene definition is sort of softly included in there. So it is going to traverse our scene, and then it's going to check and see if that ray hits any of our scene primitives. Now for that, we're going to be using programmable intersection shaders. And the reason for having an intersection shader here and making it programmable is that sort of we can use any type of primitive that we want. So with rasterization, our rasterization pipeline is designed to work with triangles. Yeah, we can send lines. With tessellation, we can send quads, but in the end, everything is converted to triangles, and rasterizer handles triangles, right? It could be handling lines directly as well, for all we care, but the point is that it's not going to be able to handle generic primitives. But with ray tracing, one of the advantages of ray tracing is that we're not stuck with triangles anymore. We can actually handle more complex objects. For example, I can directly render a sphere without triangulating it first with ray tracing. A ray sphere intersection is fairly easy to compute. So you can have different types of primitives with ray tracing, and this intersection shader, this programmable intersection shader, gives you that support. So you can use it for ray triangle intersection if you want to, but this gives you the ability to have primitives that are not necessarily triangles, right? So that's pretty helpful in general. So if my intersection shader decides that no, that ray actually is not intersecting with that primitive that I'm testing, then it's going to, of course, send it back to the scene traversal, and scene traversal will continue to find another primitive for that ray. And once it finds a primitive for that ray, that intersection shader returns, yes, yeah, I found a hit. Then the question becomes, well, is this the closest hit? Because, you know, with primary visibility, actually even with secondary visibility, I would like to find the closest object along the ray, the closest hit along the ray. Is this the closest one? Or did I already find something? Have I already found something that was closer? Earlier, maybe I found something that was closer. Then this is further away. That means it's behind that object, right? I found a hit, and now I'm finding another hit that's behind that object. That means I don't care. It's not visible. So go back. It's not the closest, so I don't care. If it's the closest, then it's good. Then I found something that I'm supposed to shade, right? But remember, one of the advantages of ray tracing is that we could handle transparency really well. So let's see if this hit, this object that was hit with the ray is opaque. If it's opaque, then it's fine. Then I can say, okay, I found my hit point. I found my hit point, then I'm done. Well, not quite. I found a hit point, and so far this is the closest one, but maybe as the scene traversal continues, I will find an even closer one. So I need to go back to the scene traversal and continue traversing the rest of the scene to make sure that there's not going to be anything that is closer. Right? So if this is opaque, that's what happens. If this is not opaque, that means it's semi-transparent. So I'm going to look at this any hit shader. So the any hit shader will determine what to do with that hit. I can say, oh yeah, I'm going to use this to just replace and update my hit data. I can do that. Or I can say, you know what, this was actually, I can use it for alpha testing, for example. I can say, oh, actually from here, you're not really quite seeing anything. So I can just pass it back to the scene traversal and ignore that hit, right? So this is what the traversal looks like. So it's a bit more complicated, and with two programmable pieces here, there's going to be this intersection shader and any hit shader if we have semi-transparent objects, right? And in the end, this hit data will stay here in the ray tracing box, and the scene traversal will need to send it to the next stage in the end. So like this is the hit that we found. That is if we found a hit. That's why this is called hit or miss shader. That's why I'm calling it hit or miss shader. Because maybe I found a hit with an object, maybe I didn't find anything, maybe it was a miss, right? So basically in this ray tracing box, I have two shaders, two programmable shaders here. I have an intersection shader and the any hit shader. And over here, we have actually not a combined hit miss shader. We have a hit shader and a separate miss shader. So if it's a hit, then the hit shader is called. If the ray does not intersect with anything, then the miss shader is called. And the result is sent back to the ray generation. So basically you'll look at it and you see that seems like we have 5 new shaders, right? Ray generation shader, intersection shader, any hit shader, and miss shader. Right. With the new tier of DXR, DirectX ray tracing, tier 1.1, I believe, now we have inline ray tracing. So you can actually start tracing rays from any of your shaders. Even in a compute shader, you can start ray tracing. You can generate a ray and tell it to traverse that ray and trace that ray, tell your GPU to trace that ray, and the GPU will trace that ray and send the result back to you, right? So you can use it inside pretty much any shader today, right? So that's what the ray tracing pipeline looks like. And we can use this. So as you can see, I'm not showing an output image here. You can use it however you like. So this is hardware supported ray tracing to accelerate the ray tracing related computations, and allows you to have programmable components here and there. And what's important is what you do in here. Like inside your shader, you are using ray tracing to do something. And this is totally up to you. So you can use this ray tracing pipeline to do whatever it is that you want with ray tracing, right? So that's where we're going to be using it, and that's how we can combine ray tracing easily with rasterization, because I could just call it from, let's say, inside my fragment shader, right? In my fragment shader, I can generate an array and just run this and get the results back into my fragment shader and continue processing my fragment shader. So inline ray tracing. All right, so that's what the GPU ray tracing pipeline looks like. Let's go back and expand this box, because I want to go back to talking about this. So we said that this box traverse scene is going to have to figure out a way to access our entire scene, right? So somehow I'm going to send the GPU my scene definitions, because I'm not sending one triangle at a time now, right? I'm going to have to put my scene into some data structure that the GPU recognizes, and then the GPU will access the parts of that data structure as needed, right? And there's actually quite a bit more going on here. This part is not all that simple. So let me explain why. How do we ray trace a particular scene? Let's say that this is our simple scene, just a teapot, and I have my ray. I have one ray. I have one ray to trace, and I'm going to figure out which triangle of this teapot this ray intersects with, if any. Maybe it's not going to intersect any of them. Maybe it'll intersect one. So we'll see. So but I have a lot of triangles here, right? Quite a few triangles. So the brute force thing to do would be to test the intersection of each one of these triangles against this ray. We could do that. But this doesn't scale all that well, because I might have a lot of triangles. I might even have millions of triangles. and I might have millions of rays. Right? So that would be quite a massive computation. So I need to find a way to accelerate that computation, and we can do that. For example, if I know the bounding box of this teapot, its bounding volumes. There's a box, the axis aligned box that covers this teapot, and this teapot is perfectly contained inside this box. Now, if this ray does not intersect with this box, there is no chance, not a possibility, that it will intersect with any triangle inside that box. Right? It's obvious. If the ray does not intersect with the box, it's not going to intersect with anything that's inside the box. So for it to intersect with anything inside the box, it needs to intersect with the box first. So by doing just this very simple computation, I can actually save a lot. Like just by adding a box to my object. Now all of these rays that would obviously miss the teapot because they're not even intersecting with the box, I can get rid of them. I don't even have to compute that. So that saves me a lot of computation. Now we can take this idea and take it a step further. I can take my teapot and, let's say, split it into two. So now I have two boxes, and I can check against these two boxes. So if my ray does not intersect with any of the boxes, then I can throw it away. Or if my ray intersects with only one of the boxes, then I only need to check the triangles inside that box. I don't have to look at the other box, right? I can do this further, right? I can split this some more, and now I have more boxes to check, but then it gives me a better level of isolating where that ray could be hitting a triangle. And I can do more, I can split it more. At the limit, I have lots of boxes. But of course, now the problem becomes, now I have a lot of boxes to traverse. So I don't want to do that. Instead, what we're going to do is that we're going to build a hierarchy from this. So bounding volume hierarchy. We're going to have all of these different levels of boxes. So at the very top, I have this one bounding box. At the next level of the tree, I have, let's say, two bounding boxes. One branch is for one of the bounding boxes, the other branch is the other for the other bounding box. So there's a root node, a child node, and a child node of the child node. So it goes all the way down to however deep that you need it to be. And using this bounding volume hierarchy, or BVH, we can accelerate ray intersection quite a bit. So bounding volume hierarchy is just one data structure, and this bounding volume hierarchy, forming a tree with two child nodes for each internal node, is a special kind of bounding volume hierarchy. It's a specific kind of bounding volume hierarchy. There are different other kinds as well, but this is the most common structure used for accelerating ray tracing today. But there are, I'm telling you, there are other acceleration structures that could be used with ray tracing. Now, what exactly the GPU does under the hood, the thing is, we shouldn't care. We probably shouldn't care. I mean, it should be good enough, and the hardware would be optimized for that particular acceleration structure, and it will do a good job in the end, we're hoping. And we don't necessarily need to care about the specifics of the acceleration structure. But yeah, it is a BVH, but it didn't have to be, is what I'm trying to say. Now, if you have a good acceleration structure, what happens is that even if you have millions of triangles in your scene, your ray you'll test intersections of each ray with, let's say, about a handful of triangles. Because this, with a whole bunch of boxes in a hierarchy, and just a relatively small number of triangles. It could be just 3, 4, it could be 10, it probably shouldn't be 20 if your acceleration structure is good. So in the end, this is called acceleration structure because it really accelerates ray tracing. Like, imagine the comparison between testing ray intersections with 1,000,000 triangles versus, let's say, 5, right? There's a huge difference in terms of performance. This is really what helps ray tracing run as fast as it does today. Very, very, very important. Yeah, a comment here is about KD tree. Yes, KD trees were very popular back in the day. They're not as popular today. I really don't want to get into the details of KD trees and why BBHs are preferred. It's a very long conversation. It's kind of yeah, it's going to be a very nuanced discussion, so I don't want to get into that. But BBHs are what we prefer today. But there might be others that we prefer in the future, maybe. We'll see. Actually, about that, we recently proposed a different acceleration structure that looks very much like BBHs. These are also called space partitioning structures because they split the space into partitions. So we proposed a different structure that looks very much like BBH, and if you have hardware support, it actually runs much faster. So yeah, maybe we'll have different acceleration structures in the future. So yeah, so this is what GPU ray tracing support looks like, and with that, we can compute global illumination. Right, so now when I say global illumination, people immediately think about path tracing. Remember path tracing? We talked about path tracing. We actually talked about a whole bunch of different ways of computing global illumination on the GPU. Now, this is not quite path tracing. This is using the virtual light idea that we discussed last time. So this is tracing some rays starting from the original light sources to place some virtual lights in the scene. And then, of course, those there are some bounces that are happening in the scene as well. So they're going to be virtual lights, even places that are not directly seeing the light source. And then the scene is rendered using these virtual lights and computing shadows and all that. Right. So maybe it might be obvious as to how we generate these virtual lights for this kind of a problem. Yeah, you can see how ray tracing could work, right? Because we're tracing rays to find where to place the virtual lights, and then we're tracing rays to figure out the shadows for those virtual lights, right? But ray tracing is a very general concept that we use in rendering, when what we use it for sampling. For sampling. We oftentimes use it for estimating this rendering equation. So you look at this equation as an integral, and it's not immediately obvious how ray tracing could help you with something like this. And it helps you with sampling. For example, if we are trying to compute the area lights for an area light like this, we could just pick some random samples on this area light surface, and then we can trace shadow rays. And with that, we can approximate the shadow. So that's going to be the idea, that we're going to be approximating an integral by using a finite number of point samples, because that's what ray tracing will do. So basically what it's going to do is going to take this integral and it's going to approximate it as a sum of finite number of elements. Okay? So this is the integral converted into a sum of, or an average of, n samples. Now it's a bit more complicated than this, because how you pick your samples becomes a little bit important. I'm sort of skipping some of the details, like importance sampling, which is super important, but I'm skipping all those details. But basically, this is the general idea, that you convert this integral to an average like this. Now, if it's not obvious to you how this works, let me show you. You can think about, like, yeah, this looks like a complicated equation, but it doesn't matter. Let's represent it as something simple. Let's say this whole thing is f. Okay, that's f, and I would like to sort of approximate the integral of this f within some domain using finite number of samples, right? So f, let's say, is a function over x defined here, and let's say this is what f looks like. It's just a 1D function. And you can think about this process as like having a finite number of samples along X, and then you compute the value of f at each one of those points. Basically, this integral will give you the area under under f over here, and this is going to give you the approximated area. So I'm skipping some of the details in the math just to make it look simple, right? So in the end, this is what sampling with ray tracing looks like. So we have an integral, we're sampling it with a bunch of rays. Now the immediate question, I think, is what is n? How many rays? Well, it depends. For example, this image from a T-port rendering competition a couple of years back. So I talked to Laura about this image. She used path tracing for this, for computing this. And with path tracing, now I don't remember the exact sample count she used, so I'm going to make it up. I believe it was something like 10,000 samples per pixel. 10,000 samples, maybe it was 100,000, but I believe it was 10,000. Actually, maybe it was way more than 10,000, but that's what I remember. It was 10,000, and that was really needed to resolve some of the details here. 10,000 samples per pixel. This is not 10,000 rays per pixel, mind you, because each ray will go through refractions and reflections. So each sample will go through all of these reflections and refractions. So each sample per pixel will correspond to on the order of maybe 10, maybe 100 rays per pixel. So even if this is 10,000 samples per pixel, it's probably more like 100,000 to a million rays per pixel. That's a lot of rays. A lot of rays. Can we do that? And why do we need this anyway? Because here's the thing. If I just use one sample per pixel with path tracing, I get a noisy garbage like this, right? This is using some very nice sampling techniques. So like the importance sampling, as I mentioned, this is actually using very nice sampling techniques, but still it's super noisy, right? I can increase the sample count to, let's say, from 1 to, let's crank it up, 1,000. Looks much better, right? From here to here, it looks so much better with more samples, but we're not quite done. You see the interior in here and there and there. It's still pretty noisy. Like in some places it worked out okay. There's still noise around here. It's not perfect, but yeah. So maybe crank it up some more. Let's say, I don't know, 8,000. Sure, it's getting better, right? So with ray tracing support, people immediately imagine path tracing, and like, let's do path tracing on the GPU. But this is the cost of path tracing. Now we can afford it for offline rendering, and that's why almost all offline rendering we have today for like movies, special effects, it's using path tracing because we can afford this. We can have lots and lots of rays per pixel. But this is what we want to. This is what we're doing on the GPU, and with this, how many rays do you think we have per pixel? We definitely don't have 10,000. 1,000? It's not even 10. It's. I think we can sort of expect to get maybe 1, and if you're lucky, maybe 2, 3. I mean, beyond 4, you're sort of pushing it. It's going to be way too expensive. So yes, we do have ray tracing support on the GPU, but this doesn't mean that we can just do everything with ray tracing because we can't afford that many rays. Right? We only have limited number of rays. So that means that what we can do with ray tracing is going to have to be limited, right? And so typically what we have in games today is about 1 ray per pixel, maybe 2 rays per pixel. Oftentimes it's even less than 1 ray per pixel. Because that's what we can afford. Because that's what runs fast. And that's why we need rasterization in here. We can't just ditch rasterization and say, I'm going to do everything with ray tracing, because, well, rasterization counts for at least 1 ray per pixel, right? For the center primary visibility, it's handling that. If I use rasterization, that means I'm going to use 1 less ray per pixel. And then I have very few rays per pixel, so it's kind of important that I do that. But you may think, okay, with 1 ray per pixel, 1 sample per pixel, 1 ray per pixel, can I even do anything with it? Like, if I were to compute some really relatively simple soft shadows with 1 ray per pixel, that's 1 ray sample per pixel, I get something that looks super noisy. I mean, that's sort of understandable, right? Because imagine that I have this area light, and I'm going to estimate how much of this area light I'm seeing by sending 1 ray. I mean, that doesn't even make any sense. With just 1 ray, because that 1 ray is going to say, yeah, you see all of the light, or it will say, you see none of the light, and there's nothing in between. So obviously we're getting noise. I mean, what else, right? So there's some probability going on here. So the probability of a random ray going to an area light, hitting something on the way or not hitting anything on the way, depends on where you are in the shadow. Yes. So this noise sort of indicates where you are in the shadow, but it's still super noisy. So what can we do? What we're going to do is going to be denoising. Yes. So we're going to take this image, generate it with as many ray samples as we can afford, typically just 1. And then we're going to run a denoiser. And the denoiser is going to work on the image space, and it's going to basically blur out all these regions, and you were going to get an image that looks like this, right? So we go from here to here. It's quite an improvement, right? In the sense that we got rid of the noise. Yeah, we got rid of the noise, and the latest denoisers are actually pretty good. Yeah, I call them like they're like magic, really. Like, you can give an image like this with lots of noise all over the place, and then you can get an image that looks like this. Right? It's like magic in a way. But of course, we are not computing this image with all these rays. So all these subtle details that we would get if we were to actually compute this image, they're all lost, right? So with ray tracing, what we can do today is going to be rasterization plus ray tracing plus denoising. And we can really generate images that look, this looks beautiful to me. I love this image. And we can generate things like this that we couldn't before. But at the same time, we kind of need to understand that there's going to be a limit to what we can do, because yeah, with rasterization related techniques, when it comes to reflections and refractions and shadows, we were sort of approximating a lot of things. With ray tracing support, we're sort of computing them, but we're not really computing them because we don't have enough rays to compute them. So we are doing this denoising in the end. So we are sort of approximating the actual computation in a noisy way, and then we are having this denoising pass, so we get something that is usable, right? And that's the reason why, that's one of the reasons why when you look at images like this, they may not look perfectly real, because we're not actually fully computing them. We're sort of approximating them, right? That's one of the reasons why the images that we see generated using rasterization plus ray tracing on the GPU, even though we're using ray tracing and we're sort of expecting everything to look just real. They don't quite, because we don't have enough rays, and we're sort of using this denoising step to make things look okay. Now I'm going to show a reference here. This is a Siggraph 2018 course, Introduction to DirectX Ray Tracing. If you're interested in implementing ray tracing, I would really highly recommend that you check it out. The video is available on YouTube. You can watch the entire, I believe, 3-hour course. And here's a link. You can find this course in this link under Chris Wyman's webpage. I would really recommend it if you want to implement ray tracing. Go and check out that course. It's excellent. It covers the basics of ray tracing, as well as all the details of the API and writing the shaders and everything. So I would really recommend it. All right, so this is what I wanted to cover regarding where we are today. Now, I also want to say a few things about what we should expect the future to look like. Now, any prediction of the future is sort of doomed to fail because, you know, like, there are things that, I mean, maybe you can predict certain things, but definitely you cannot always predict everything, and some things can be big game changers. So I'm going to say a few things, but before I say anything, I just want you to take it with a grain of salt, because I know that, you know, there are only certain things that I can see, and there are things that I won't be able to see. So my predictions of the future may be quite off. So we'll see. Maybe I'll be spot on, but maybe I'll be really off. But I'm going to base my prediction on a history. This is oftentimes a good idea. If you see how things worked in the past, that might give you an indication of how they might work in the future. And I think the history of offline rendering is a very good indicator of what we should expect to see in interactive computer graphics in the next decade or so. So in offline rendering in the past, ray tracing was in a similar state. We were using in early days, we weren't using ray tracing at all with offline rendering. Everything was just rasterization. It was not Z-buffer rasterization necessarily. We were using A-buffer because A-buffer could do transparency a bit better than Z-buffer, quite a bit better than Z-buffer. So it had that advantage. But beyond that, you know, there's rasterization-based algorithms. Pixar's RenderMan has been using Reyes, again, another rasterization-based algorithm. So we had rasterization. And in the end, we added support, ray tracing support, just a little bit of ray tracing support for handling reflections, for handling refractions. And then we extended our ray tracing support a little bit. And then in the end, we started computing global illumination with ray tracing support. Actually, talking about history, I just want to mention the history that relates to me, that I had implemented a renderer for global illumination back in 2002, 2003 is when I had implemented as a part of my master's thesis, and then I published it much later. This is a global illumination-based rendering. So there's just one light source in the scene. Everything is illuminated by the single light source, and the whole scene, pretty much the whole scene, is rendered using indirect illumination. And there is no ray tracing here. This is pure rasterization. And I'm telling you, this is a bad idea. Don't do it. Back then I thought this was, oh yeah, ray tracing is too slow. We can't do ray tracing. So let's do everything with rasterization. That was my idea. And I did that. But I think if I were to do this in ray tracing, it would have been faster. Even back then. So not necessarily a good idea. What I'm trying to say is that even for offline rendering, ray tracing was really, really slow at first. So we didn't quite use that, and we started doing stuff. We started adding things as we needed them. So we started with rasterization using A-buffer or Reyes. and with reflection maps. So for if you want reflections, we were computing reflection maps, just like the render to texture tricks that we've been using in this course. They were used in offline rendering back in the day. And then we had some ray tracing software. So we had, of course, software. So we started using rasterization plus ray tracing. So with perfect reflections and refractions, we could use ray tracing. And with hard shadows, instead of computing shadow maps, we could use ray tracing, right? So this is very close to where we are today with real-time rendering. But that's where offline rendering was about 20 years ago. Approximately, but that's where we were. And of course, we had a few other things, like maybe we could do soft shadows and global illumination. And so what happened is that as the rendering software evolved and the computers became faster and faster, we moved from rasterization only approaches to rasterization plus ray tracing, and then to ray tracing only. And ray tracing only. And today we're using ray tracing only. We sort of ditch rasterization completely for offline rendering. For the most part, rasterization is very, very rarely used. Almost everything is rendered only with ray tracing, including primary visibility. And let me tell you why that is the case. So, because let's go to a comparison between rasterization and ray tracing. What would I use for anything? For primary visibility, what would I use? Ray tracing or rasterization? I could use both. That could work, right? For shadows, what would I use? Ray tracing or rasterization? Well, yeah, I could use both, but shadow maps, they will have resolution-related limitations. They won't be able to handle area lights very well. So maybe with shadows, we want to stick with ray tracing. Ray tracing will give us better shadows, no question, right? Reflections and refractions. I could use rasterization if my object is perfectly smooth and if I'm okay with approximating it. But for general reflections, especially for surfaces that are not perfectly smooth, I want to be using ray tracing, right? I don't want to be using rasterization. For global illumination, oh well, I have to use ray tracing. There's nothing else. Okay, so look at this picture. All of this stuff, I need to use ray tracing. Primary visibility, I can use rasterization or ray tracing, right? Now here's the thing. When you have enough rays to compute these things to the quality that we want, what is one more ray to handle this? If I'm going to have, let's say, 1,000 rays per pixel, what is 1,000 plus 1? Right? I can just use 1,000 plus 1 and get rid of this. And then everything becomes ray tracing. And when I do that, then I get rid of all of the limitations of rasterization. Now, all of a sudden, my polygon count, my triangle count is not a big deal because I'm dealing with ray tracing now. And I don't need to worry about transparency. Transparency is very easy to handle. I don't have to worry about transparency at all, right? So my prediction for the future, based on this picture, is that when ray tracing is going to be fast enough, so we can compute global illumination using the techniques that we want to compute, so that we have, I don't know, on the order of 100 to 1,000 rays per pixel, and we can handle that, then I'm going to say we probably won't need rasterization, except for maybe some special cases. There might be a few cases where rasterization will be just perfectly fine, and we can still, it doesn't take that much area on a GPU chip, so maybe it's okay to keep it around. But I'm expecting the graphics API for interactive graphics to be mostly, if not purely, on ray tracing when the hardware is fast enough. So when is it going to be fast enough? Well, maybe for that, we need to look at hardware that is designed for ray tracing and ray tracing only. So today's GPUs are designed for mixed rendering, rasterization plus ray tracing, because with only ray tracing, we can't do as much as we want. It's very limited. But we are looking into that. at the University of Utah, we have a hardware ray tracing research group. And we're designing the future GPUs around ray tracing only. And we're sort of modifying the ray traversal software, and like we're modifying the ray tracing from a software perspective in ways that make no sense for existing hardware. But then we're designing hardware that's specialized for handling that sort of ray tracing, so we can have super fast ray tracing based GPUs that can only do ray tracing and nothing else. So that's one of the research projects going on at University of Utah. And who knows, maybe in the future, not so distant future, we'll get there. I'm hoping within the next decade that we won't have to use rasterization at all for interactive computer graphics, and everything will be ray tracing, because I think it's objective to say that ray tracing is vastly superior to rasterization. It's just that we have very super fast hardware for rasterization that our ray tracing hardware currently cannot compete with. And without that super fast rasterization hardware, we would not have interactive computer graphics. So don't undermine rasterization. This is how we have interactive computer graphics. Without that, we wouldn't have interactive computer graphics. We had interactive ray tracing for a couple of decades now, but they're not delivering the performance of rasterization. So interactive computer graphics still stands on the shoulders of rasterization. So we are in a very interesting place in computer graphics. Now I gave you this history of where things were at on offline rendering, and I'm trying to draw some parallels, but it's not possible to draw direct parallels because computer graphics evolved. We have much better algorithms than we didn't have before, back when offline graphics was dealing with similar issues in terms of performance. So we can do a bit more with the ray tracing capability that we have on the GPU than we could do in the past with similar form of limited ray tracing that was available in offline rendering, because we have new algorithms. We have a lot of new inventions, a lot of new and ingenious ways of using this limited ray tracing power that we have. And actually over the decades, since the programmable shaders were introduced, people figured out all sorts of interesting ways of using this hardware, or dare I say, abusing this rasterization hardware to do things that it really wasn't designed to do. And with that, we could get all sorts of interesting algorithms, and we could do things that we couldn't do before. And in this course, we talked about a lot of those examples, actually. A lot of rasterization-based algorithms that use the GPU in ways that GPUs were not quite designed to do. And that was totally fine. So now that we have ray tracing support on the GPU, it sort of gives us this additional tool that we can add on top of all the collection of tricks that we have in real-time rendering and interactive computer graphics. Now, ray tracing is an additional tool in our toolbox that we could do more. So we don't have to just take ray tracing and implement the same algorithms that are used for offline rendering. We can do interesting things with them. So yes, we can use them in forward rendering or deferred rendering. We can use them in our fragment shaders to do things that are designed for ray tracing, but we can do other things with this interesting tool that's available now. And today is the time for those sort of inventions that are coming out every day. So this is the time for those sort of interesting things, interesting tricks to come out. And they are coming out. Okay, so I am going to end it right here. Thank you again for joining this interactive computer graphics lecture. Stay safe. Bye. Thank you. Oh, thank you.